Thank you for giving us this opportunity to present the work that we have been doing on providing efficient communication for dynamic first responder teams in emergency response. I'm KK Ramakrishnan from the University of California, Riverside, and this is a project I've been working closely with Jiachen Chen from WinLab at Rutgers University. We have all seen often that communication is key to managing a disaster. It is a critical component for improving outcomes and saving lives. The key for an effective incident response is to be able to not only have communication within the organizational structure, but also among dynamically formed first responder teams whose members might come from different departments, for example, law enforcement, firefighting, EMT, and others. We might also need to accommodate a number of other people depending on the particular incident. For example, in the past, we carefully studied the London bombing response. The key there for helping people was to be able to bring the team of people who are managing the subway system in London to be part of the first response team. So we want to enable bringing in organizations that might not usually be part of the first responder environment together in a dynamically formed first responder team and provide efficient communication for the incident command chain. We also realize that when you do have a disaster, for example, a hurricane or earthquake, you might have infrastructure that is impacted and communication channels might be disrupted. In some cases, the channels, although still functioning, may be congested due to high communication demands, and we want to be able to deal with those situations as well. Our primary objective is to create an architecture to provide timely, efficient, and resilient information dissemination in managing the disaster. In this architecture, we first create an information layer to facilitate the communication among dynamically formed first responder teams. The network layer below it enhances the robustness in message dissemination in both infrastructure-supported and infrastructure-less environments. The application layer at the top provides the basic functionality and enhancements desired by first responders. We see that a number of organizations that are responsible for handling incidents, whether it is police, firefighting, or others, they have organizational structures within their departments. They may also have their own means to communicate amongst each other. What we want to do is to see how to bring these organizations together in a dynamically formed team, enable them to have a free exchange of information along the newly created incident commander chain based on the nature of the disaster. We adopt some of the concepts related to information-centric communication, which is driven by a name-based framework as the foundation. We created an information layer on top of the traditional network layer we are used to. In our design, we use structured names as units, departments, and roles, and set up an effective communication framework not only based on the predefined a priori well-known organizational structures, but also dynamically created roles and command chains which are completely independent of where the units are located, both physically and in the network. In this layer, the design of the structured names, that is the namespace, is the key. Some of us are familiar with how DNS works in the internet, which is for the most part hierarchical in nature. But when we look at how information is organized, and also in the context of how people are organized, we see a directed graph, since there are multiple dimensions for each aspect, although in each dimension it may be hierarchical. Think about a particular firefighting department, like the New Jersey Fire Department in the example. It might have a location dimension, a functionality dimension. It might also have a dimension based on the fact that it is involved in a particular incident. Particular individuals may be responsible for a role during one shift and someone else for another shift. While designing the namespace, we want to embrace all of these rich characteristics to better reflect the relationship among first responders in different command chains. Our namespace design goes beyond the traditional simple hierarchical namespace as we are used to, whether it is DNS or in the more recent information-centric architectures like named data networking. In those solutions, in order to represent the multidimensional relationships, we end up having to duplicate the names. That results in scalability issues and overhead in management. Imagine dispatching units to specific roles. We would have to create new names in the namespace and ask the affected first responders to listen to these new names. In our design, we accommodate a graph structure. It allows us to have multiple dimensions for each node in the namespace and helps us in dealing with the whole issue of communicating among these dynamic teams. Importantly, we allow the namespace to be dynamic with nodes and edges that can be dynamically added or removed with very little overhead. We will show it in the following technical demo. Within this graph-based namespace, timeliness and relevance of the information delivery are important. The useful service interface that helps us here is a publish-subscribe capability because it separates the temporal coupling between publication and the expression of interest for a particular piece of information. We use a shared multicast structure in the network to allow multiple publishers to send messages to the same name. Now let's look at how first responders can use the information layer for efficient communication among dynamically created teams in an incident.
In this demo, we have an incident commander, a dispatcher, a field officer that are using PCs or tablets, and a set of first responders who use smartphones for communication. These units belong to different departments. To reflect the organizational structure, we have pre-built part of the namespace, and it is visible on the GUI of the dispatcher. To distinguish the types of names, we use a yellow color to represent the departments and the first responders, and a blue color for incident-specific roles, and we'll see that soon. The devices would subscribe to corresponding names when they're assigned to different units that are instantiated within the organizational structure. For example, this device would subscribe to the name EMT2 when the user logs into the system using the credential of EMT2. Similarly, each device has subscribed to the name of a first responder as highlighted. Now, the first responders can send and receive messages within their organizational structure in their daily duties. For example, we can send a message to Middlesex County, meaning that we want to notify all the first responders in the Middlesex County. The message would be propagated along the direct links in the namespace and reach Middlesex EMS Department, Middlesex Police Department, and Middlesex Fire Department, and eventually reach the units in these departments. If we send a message to fire instead, meaning that we want to notify all the firefighters, we'll be able to reach the fire departments in Middlesex County and Union County, and eventually reach the firefighters in these departments. You can see that with the graph-based namespace, we only need to create one name for Middlesex Fire and its descendant names, although they belong to two hierarchies in two dimensions, namely geolocation and functionality. We'll show this message delivery in the incident later. Now, let's assume that the incident commander has to deal with a search and rescue mission in Ridgecrest due to an earthquake. He can initiate the task by instantiating a template or a pre-plan. Here, we have pre-coded 3 templates according to the National Incident Management System, or NIMS. Each template comprises a set of roles to be acted by one or several first responders, and a command chain based on these roles. We assume that the emergency response departments will digitize these templates for each type of incident when they're making pre-plans for these incidents. So, when the search and rescue mission starts, the commander can simply pick one from them. We use search and rescue here as an example. The commander then gives the incident a name, Ridgecrest, and click the instantiate button. Our application would automatically create a set of names and corresponding relationships in the namespace. The incident commander can then request the dispatcher to send some units for each role that he needs. To do this, he can send a message that describes the requirement and put the roles in the attachment. Let's assume that we need units for the 3 roles highlighted here. Once the dispatcher sees the message, he can click the roles to show them in his own view. To perform dispatches, he just needs to drag the roles to the units. For example, let's dispatch tech support as Rescue Squad 1 officer. We see that once the dispatch is done, both the incident commander and the involved first responder will receive a notification immediately. Thanks to the graph-based namespace, no name needs to be created here, nor does the first responder need to subscribe to new names to reflect the assignment. All that we have modified here is a new relationship in the namespace. This minimizes overhead to both the management and the infrastructure. Similarly, let's dispatch Rescue 2 and Firefighter 1 as Rescue Squad 1 specialists. The dispatcher can also assign a whole department to a role. For example, let's assign Bridgewater Township EMS to medical specialists. You can see that the structure is revealed in the view of the incident commander, and every unit in this department is notified about the assignment. The incident commander and the first responders can now use the namespace to send messages to different groups of people at different granularity. For example, a message to Rescue Squad 1 will reach 3 first responders in the group, and a message to Ridgecrest will reach everyone dispatched for this incident. In short, the messages will be propagated according to the direct links in the namespace to all the subscribers below. In our application, we enable both text messages and push-to-talk that are already very familiar to first responders. Here, let's assume tech support is going to send a push-to-talk message to medical specialists. He can find a role with a simple keyword search, and then press the PTT button to record the message. Once he releases the button, we see that EMT1 and EMT2, who are assigned as medical specialists, receives it. A benefit with the role-based communication is that the communication parties do not have to keep track of which units are currently in a particular role. Let's assume that when changing shifts for a Rescue Squad 1 officer, the dispatcher tries to replace tech support with field officer. He can do it with some simple drag and drops just like before. The affected units will receive corresponding notifications. The incident commander can also see the shift in his view, but he doesn't have to worry about it. When he sends a message to Rescue Squad 1 again, the field officer will receive the message instead of tech support. The duty shift is performed seamlessly.
To deal with infrastructure disruption, we support device-to-device direct communication, complementing the regular infrastructure-based communication in the network layer. It allows first responders within a partitioned environment, for example, a shelter that may be cut off from the rest of the environment, at least in terms of communication, to be able to communicate with each other. We also need to accommodate the occasional communication that may be available to points outside the partition, for example, using a data mule or intermittent or carefully managed satellite access. We support D2D communication using different link layer technologies like Wi-Fi direct, Bluetooth, and LTE direct and 5G direct communication.
With the help of D2D communications and the store and forward enabled routing protocol in the network layer, we allow the application to operate in infrastructureless environments, for example, a shelter. When the shelter is not far from the coordination center, or one of the devices can reach the internet via satellite or LTE, this device can act as a relay and all the messages can be delivered immediately. If the shelter is not reachable, we can have a data mule, for example the patrol car in this demo, to carry the messages and updates to the namespace back and forth. First, let's mimic the change in the topology by disconnecting the patrol car and rescue one from their Bluetooth link. When the commander sends a message to Ridgecrest now, none of the units in the shelter receives it since they are physically disconnected from the coordination center. However, this message is buffered on the patrol car. Now, let's assume that the patrol car has reached the shelter. We mimic it by disabling the Wi-Fi connection on the patrol car and reconnect it to Rescue 1 via Bluetooth link. You can see that the moment the Bluetooth link is established, the units in the shelter receive the message from the commander. Similarly, when the units in the shelter want to deliver messages to the incident commander or make some changes in the command chain, the updates can be carried back to the coordination center by the patrol car. We skip this step due to time limitation.
With basic text message and push-to-talk functionality provided, we also added some enhancements in the GUI based on feedback at a few trial exercises we had with first responders. These enhancements aim to save time and effort for first responders that is spent on communication. For example, a receiver does not have to ask the speaker to repeat if he did not hear a message clearly. Also, that person can choose to focus on a task and come back to the interaction later. The speakers do not have to wait for acquiring the floor and synchronize their speech and things like that. Let's take a look at some of the technical demos on these enhancements.
When a first responder receives the PTT message, "Bob, I believe Tech to Protect will make a valuable contribution," our application performs speech to text. If the user did not hear the message clearly, he can look at the text. In addition to speech to text, we also store the message audio received. If the text is still not clear enough, the user can replay the message by clicking the message body instead of asking the sender to repeat. Bob, I believe Tech to Protect will make a valuable contribution. Since we store the messages, they will be available for future use, such as supervisory review, evidence, etc. Similarly, we also support text-to-speech. On receiving a text message, our application can synthesize it to voice so that the first responders can operate the application eyes-free. Now, let's assume that a first responder wants to focus on the task and come back to the interaction later. He can click the Do Not Disturb button highlighted on the screen. When in the Do Not Disturb mode, the received PTT messages will not be played and shown in the green color. Although the message is buffered, our application still turns it into text so that the user can take a quick glance if he has time. The user can also allow some units to override the Do Not Disturb mode by long-click the Do Not Disturb button. Currently, we allow emergency messages to override. Now, let's add Commander Add into our override list. Now Commander Add is added to the override list. We can see that the message from another first responder is still buffered since he is not on the override list. But when Commander Add wants everyone to evacuate, his message will be played immediately.
Team 1, evacuate immediately.
When Charlie finishes his task, he can exit the Do Not Disturb mode. The pending messages will be played one after another. Are you going to participate in the effort on November 15th? Now, we use three first responders, Bob, Charlie, and Ed, to show that they can send PTT messages without the need to synchronize. Our application would serialize the speech and prevent them from overtalking each other. This would be particularly useful when the channel is busy or the first responders are using links with long delay, for example, satellite. Now, Bob is going to start his long report. Both Charlie and Ed would hear the message.
From Bob, firefighter. We have an incident that needs EMT support. There are 3 people needed to be rescued.
Now, Ed just pressed the PTT button. The playback on his side will be paused so that he can record the message to send.
From a house fire.
Charlie,
the 2 adults were upstairs and the third, child, was down.
Now, Ed releases the PTT button. The outgoing message is buffered and the playback of Bob's message continues. You can hear that the playback on Ed is about 4 seconds behind that of Charlie.
Downstairs in the living room. The 2 we had to go in and rescue the child first, who was okay. Downstairs in the living room. The 2 adults upstairs are suffering from some burns and smoke inhalation. Who was okay.
Now, let's assume that Bob just finished the report. The application on Ed will find out that the channel is available. It will send the buffered message while still playing the message from Bob.
Location. Please let us know as soon as the ambulance is on its way.
And support Bob. The overtalking is prevented automatically. In the view of the dispatcher, other than organizational structure, we also added a panel to show the geolocation of the first responders. The group management and the unit management panels are added on the left to simplify the dispatching process. We allow the dispatcher to locate a unit so that it will be centered in the view. Similarly, by clicking the locate button next to a group or a role, all the units dispatched to the role will be shown in the map. For units that are currently offline, we show the time and location of his last check-in. To dispatch units in this view, the dispatcher only needs to select a role and click the Add or Remove button next to the unit listed. The units can then communicate using the new command chain.
To sum up, we see that communication is key to saving lives in disaster management. The 2 main challenges to provide efficient communication in this context are: teams are dynamically formed, which might even involve personnel that are not usually part of the first responder environment. We might face infrastructure that is impacted, or the channel could be congested in the aftermath of a disaster. In this work, we proposed a layered architecture to deal with these challenges. The information layer takes the concept of information-centric communication to allow first responders to communicate based on roles, independent of the user identity, their geolocation, or the location in the network. A graph-based namespace helps to represent the dynamically created and evolving teams with very low overhead to both the first responders and the infrastructure. The network layer takes advantage of device-to-device communication for resilience, especially in infrastructure-less environments. At the application layer, we support both text messages and push-to-talk, which are already familiar to first responders. Based on feedback from them, we also added enhanced features like speech-to-text, text-to-speech, message replay, do not disturb, asynchronously sending messages, and so on. The map function also helps dispatchers to visualize the location of units and allocate resources efficiently. Thank you very much. We're happy to answer any questions you may have.